I think one of the problems is different people have different emails for me, and so I never get a solid message.
Yeah, that's true. I feel like I searched her name and I got your Gmail.
Possibly, but I
Pretty recent.
think it's on the website. I think it's now has my SIU.
Or like I like in my email send thing, like the first one that popped up, I think was your Gmail instead of your. It was kind of weird.
Hi, Zoom.
Yeah, no one is there. Oh, it's supposed to be 4 of us there. Talia, Jerome, Khaled, and Michael. Yeah. Jerome there. Talia. Your homework 9. You Friday. I heard homework 9 seems considerably easier. That's what Rob said. I didn't get it.
A little bit more straightforward.
Straightforward. That's I think that's probably true. It should be because I couldn't come up with more than that. I don't verify this conversion. Next Monday we have an exam. Only 3 weeks of classes, so that's 6 classes per month. One of it is an exam, so 5 classes. The 16th is Monday.
So you know how to take home exam?
Yes, this is going to be a take-home.
So will we meet on that day or no?
Oh, good question. I have been trying not to meet, but unless it's good for me in the sense that I get to cover one more. But I also felt that it gets overwhelming for you guys. I think you guys are being too much, what's the word, bogged down with things to do. At least that's the impression I got 2 weeks back, that you were all under too much pressure about. I mean, I understand that you guys are involved. So I don't mind not taking a class, but if you guys want to, you can meet, even if it's just a gathering, that's also perfectly fine. I think, yeah, that was during the math methods exam, right? And so all of you guys chatted, so that's also perfectly fine. So let me know what you guys want to do. Is there any suggestion?
Um, Probably not cover new material.
Okay. So just come to the class without any agenda, is that your point? I heard you don't not to cover new material, right?
Right. Well, I mean, if coming to class would be useful for like exam questions or stuff.
How about this? I will be there in the class or Zoom, however you guys want me to. And if no one shows up, no one shows up. If someone shows up, that's up to you guys. No, no requirement at all.
Uh-huh. Okay.
Reasonable?
Yeah.
Yeah. So that way, no one is bound to. But I will see that. Since it is going to be, so since there's a chance that no one might show up, I won't come to the class. I'll be on Zoom.
That's fine.
Right, I'll be on Zoom and with writing more and all things. So, yeah, take on no class. Right? So no class. That'll be available.
And I was curious, since there will for sure be no meeting, I guess we don't re-adjourn after Thanksgiving break.
No.
How will the final exams work? They'll just be a take-home exam, or we'll take them.
Yes. By the way, after Monday, we do meet on Friday, right?
I think so.
Yeah. So we do meet on Friday, November what? 20th. And your point was regarding final exams, so that's the next thing. So I did look up. Final exam is on December 9th. If one of you guys could check sometime when you get time, verify that I did get this right. So this is officially it is to be between 2:45 to 4:45 p.m. And remember, this cannot be in class. This is like after Thanksgiving, university is closed for classes. So we will again make this take home. Like this will be a proper take home. Most probably it will be available during the weekend before exam. So the exam is on Wednesday, but it will be available if I have everything prepared even on Friday, but most probably during the weekend. So by weekend it's available, but it has to be Q4:45. Cannot be. So that becomes a strict deadline. That's the same thing with anything that is being submitted. It's any submissions has to be done before the Friday, the last working or last week of classes. On Friday, let's say 12 p.m. Everything should be. That's the wall. If you cannot cross that. And was that your question, Jordan?
Yes. Yeah, that's kind of what I was asking. I figured it would be that way, but I wasn't sure, you know.
So yeah, so due at 4:45 p.m. Probably write it. And more important, all submissions, right? Also, if there are any late submissions, as of now, I haven't analyzed any late submission, but those are all because they are 1 or 2 days. Nothing has been significantly delayed. But from this point on, since at least there has been homework 8 or something, just 1 week late, but that's okay. I don't know how I'll take fairness into account. If everyone has submitted, you are only one, then I might penalize a little bit. But I would encourage you guys to submit anyway. But whatever it is, it has to be submitted by December 4th. I think December 4th is Friday. 4 plus 7, 11. Okay. Any other questions? Okay, so we were trying to understand the content of Kramers-Kronig relation, and we introduced it, but we want to make it more concrete today. So Kramers-Kronig. The idea is that if there is any response, we are thinking of a response in the sense if there is a polarization and if there is an induced polarization due to the electric field applied, then the vector P, but you can think of it even as a scalar. So a response is related, let's say PT prime and minus infinity to T and chi T minus T prime. If you put a vector here, those are electric field and polarization, but we want to think of any response. So this is a cause and this is an effect. And this is a very, like since the time of Faraday, during Newton's time, this was not looked upon like this. The interactions between objects was not looked as on as cause and effect relations, but it was only during the time of Faraday. Faraday was the first person who started the interpretation that some cause happens and the effect is mediated typically by an intermediate entity, let's say. At this point, I'm having light in mind. But without any implicit details, we have a polarization or any effect can be thought of as a cause and effect situation. In the Fourier world, this looks like E of omega, the frequency, is equal to chi of omega. Maybe I should clarify something before that. This chi here has to be can be also thought of as theta of t times f of t. So write the material property that decides the effect in terms of a causal structure, and in that case you can write this is minus infinity to plus infinity dt prime. In fact, this should be f, right? Because if I write f, then I don't need t, and if I write in this form, I don't know if the time limit there, the limit on the time integral, but this has the property that it cuts it off. So that's how it looks like in the time space, but in the Fourier space, we showed that this is significantly simpler because of this translational symmetry. It's just simply omega. And the advantage is clear. This is algebraic, that's an integral. It's clearly much easier to work in the Fourier space. But that's not the only reason why it is why you typically work in the Fourier space, because the measurements are actually done in terms of frequency. Typically, these are done for light, and you make measurements for different colors of light, red light, blue light, and so on. Okay, so that's your response, and we want to now study what is chi. This is polarization, real quantity, electric field is real, so you would like chi to be real. So first condition we put is that chi is real. And so then the question comes, if chi is real, theta is also real, right? It's a step function, so that implies that f is real, f of t. So maybe I should specify t, right? F of t is real. And then we would like to ask, what about f of omega? Like if a function is real, what does it mean? What is the condition it imposes in the Fourier space? So let's say f of t is equal to minus infinity plus infinity. That's the Fourier transform. Omega over 2 pi e raised to minus I omega t f omega. Notice I use the same function, but these are this is understood that this f and these are different functions. Fourier transform need not be the same function. It is real, that means I can take the complex conjugate and it's the same. F of t star has to be equal to f of t itself, but what is f of t star? This is a sum. If I complex conjugate something, this minus infinity plus infinity d omega over 2 pi. The integral is nothing but a sum of x plus y plus z star. Each term gets complex conjugated. So this is the same as minus infinity to plus infinity d omega over 2 pi e raised to I omega t now plus I omega t, and f of omega star. There's no necessity that f of omega has to be real. So what can we do? This has to be equal to this, right? These two has to be equal, but that's hard to see because these vectors or eigenfunctions are not exactly in the same form as that. So that we would like to write it as much as possible in terms of the same format. So let's substitute, this is an integral. Let's substitute omega. Let me change this, right? So this is an integral variable. I can change this to omega prime. All the omegas to omega prime. And then let's substitute omega prime is equal to minus omega. Or I start with omega and then substitute minus omega prime. And then I'll rewrite omega prime back. This means d omega prime is equal to minus d omega. And my integral becomes, when omega prime is minus infinity, omega is plus infinity. D omega prime is minus d omega. And this is minus I omega t. And omega prime is minus omega star. I use the negative sign to change the order of integration. It's minus infinity to plus infinity d omega. Good. So that's your f of t star, and the first line gives you f of t. Those two are the same. Here, f of t is equal to f of t star. That's the condition for reality. That means the first line has to be equal to the last line. It's minus infinity to plus infinity, d omega over 2 pi e raised to I omega t. F of omega has to be equal to d omega over 2 pi f of minus omega star.
Those should be e to the minus some I omega t, right?
Oh, yeah,
On
yeah,
both
yeah.
sides.
Yeah, I think I was looking at this. Yeah. And typically in positions like that, it's plus times this is minus. Okay, so what can you say from this equation?
So there's few, like, since it's going to be in positive, visual, say,
Not the mean.
No.
but it'll always have this feature in
Where do you need to meet yourself?
analytic function.
I think that's me speaking.
It is,
Yeah,
but he's
that-
probably
that-
watching all of this.
I see.
Oh, that's my fault. I had open tabs of YouTube and I just realized the YouTube was playing in the background. So you guys may have been picking up the audio of you speaking your lectures on YouTube. I couldn't hear it, so I'll close that tab.
Yeah, no problem, yeah. Yeah, it's less embarrassing than many other things that happen.
I actually couldn't hear it, so, but it's probably me because I'm on my computer and I have like 3 tabs open from the lectures. So I see
Sure.
one playing.
Yeah, no problem. Okay, so we want the function to be real. So that puts in the Fourier space, this is the condition we can obtain. But what does this mean? What's the next step you can conclude from here?
F of omega equals minus.
Very
F
good.
of minus omega star.
Very good. And why is that? I've done this many times, but I would like to see. Just checking in here. That's correct.
Can we like write f star omega equals f of minus omega? I like it that way.
From here, you would say this, right? I see what you're trying to say, but first let me get into this. So why is this true?
They have the same coefficients. And the-
Same
the-
components.
Yeah, so if you think of, so this is a complete set, Fourier space is a complete set. If you think of this as eigenfunctions, its coefficients has to be same on the left and right, simply because it's a complete set of functions. Okay, good. So that's good. That means, but Avinash wanted to write it in a slightly different way, but this is good enough. This is how, if there is a Fourier transform of a real function, it has to satisfy this. But I can take a complex conjugate again, right? Let me say f of omega star is equal to f minus. That's also good enough. Either way is good. So this implies that f of omega star is equal to minus. So that's something we learn about this. So this susceptibility function is built out of chi, but we don't know yet how it looks like in the Fourier space. This even this is a question, right? This is a product in time space. How does it look like in the frequency space? When there was a integral, it became a product. So a product probably, we don't know yet, will become an integral. Right? So usually there is an inverse nature in this transform. So this in the Fourier space is going to become convoluted. This is called a convolution, Fourier convolution. So this might be a Fourier convolution, and we at least know that f is having that structure. Let's go slow, we'll reach there. Second, now when you say this to be the function chi, this is equal to f of t when t is greater than 0, but it is 0 if t is less than 0, right? But this 0 gives it a lot of freedom in the sense f of t could be anything there in principle. If I open the structure of f of t for t less than 0, I could choose anything because the step function anyway is going to kill it. So I have a choice. There's an arbitrariness in the function f for t less than 0. So you choose. So this is not a requirement. You choose. And which also means that whenever there is a human choice made in any analysis, it should always be shown that your result should be independent of the choice. That should always be the case. We won't do that here, but in principle, that can be done. So choose f of minus t to be equal to minus of f of t. Means we make it an odd function. So that's again a structure we are putting in the time space. Then we ask, how does it look like in the frequency space, correct? So we have to go through this again and ask, how does it look like? So let me erase one of these things. So this time I just have to do f of minus t. So f of minus t is equal to minus infinity to plus infinity e omega over 2 pi. Minus is simply I omega t. The same thing as earlier. Again, I make the same substitution. In fact, I can make omega prime here right away. Omega prime is equal to minus omega, and this becomes, this time I don't do it in 2 steps, I'll do it in the same step, e omega over 2 pi. This is minus I omega t, and f of omega prime is so it's minus. Okay. We have f of minus t, f of minus t to be equal to f of t, sorry, minus of f of t. That means I substitute the two relations, minus infinity plus infinity, e omega over 2 pi. Minus omega, and this is equal to minus of f of t, which is the top line. Again, these two have the coefficients of this eigenfunctions has to be the same because the Fourier space forms a complete set. So this implies f minus omega is equal to minus of f of omega. It's pretty much the same as that. It's very similar, that nature. So if a function is odd in the real space, the function, which is a complex function, it has a real part and an imaginary part, that together is an odd function. So this is equal to so f of minus omega is equal to minus and the third requirement we put is that what is the Fourier transform of theta, right? So what is theta of omega? So the question mark is what is theta of omega? So we just find the Fourier transform of that. So, any questions as of now? Okay, so step function of t is equal to minus infinity to plus infinity omega over 2 pi omega, correct? That's your definition of the Fourier transform. So we would like to know what this is. So I want to invert this now. The inverse Fourier transform is the same, except there's no 2 pi and the sign of the eigenfunctions changes. Correct. That's should be quite good enough. But we know the step function. This survives only when t is greater than 0. It is 0 otherwise. So that puts a limit on the integral. The t has to be greater than 0. Anytime that dt is the lower limit that is putting the conditions. It's 0 to infinity dt. T equal to 0 to infinity. So t will always be greater than 0. That's it. And I think if you remember, we encountered this, or we did this example in math methods also. And what's the integral? What's that integral? What is that integral?
So delta omega? 2 pi delta omega?
That's minus infinity to plus. This is 0, right? So if it is minus infinity to plus infinity exponential I omega t, then it's formally a delta function, even though it's a little sensitive or say, if you want to prove it, it use very delicate identities. So what is that integral equal to? It's exponential. One would think it is very straightforward. So
Into the I omega over I omega minus 1.
yeah, so this is e raised to I omega t over I omega, right?
Mhm.
And then you evaluate this at t equal to plus infinity, t equal to minus infinity. And what is that?
T equals 0.
Huh?
The lower limit.
Oh, t
0.
equal to 0. Yes. Okay. And what is that?
Is there like some standard form for it?
No, it's
This is
it's ambiguous,
I omega
right?
over I omega minus 1.
Yeah, it's
Minus
ambiguous
1 over
because it's an oscillatory function, right? All the way at infinity, we really don't know what happens. So it's ambiguous. You cannot do this integral. Right? So this is an undefined integral. So we are stuck here, right? So it's step function. We just said it's straightforward. Well, one would think it's a straightforward function. It's not really, right? It's not a nice function in the sense of the word. So this here you get stuck, right? So we have to do something. We have to get creative. So one of the simple things you can do is we can do this using complex contour integrals also, which we showed in math methods. But we will do poor man's methodology, which is pretty good, right? So this is not defined. So we want to. This is called regularization. What? No, regularization. Yes. This is called, this kind of methods are called regularization. We used to be able to. I struggled with that. Yeah. Regularization. Yeah. So basically, this is an undefined integral, but do something to it so that it becomes defined in some regime. That means I want to converge it, right? We saw that it is oscillatory. So think of that harmonic oscillator, right? Harmonic oscillator keeps oscillating, but if you keep a damping term, it will go away, right? So put a damping term in it. And how would you put that damping term? So this is dt e raised to I omega plus I delta times t. And what does that? So I put a delta, that's not the same, so I want to put the limit delta tends to 0. And it has to be 0 plus. So how does that make it any better? because notice that this is exponential of I omega t. That's still oscillatory, but I and I minus, so that's a minus delta t.
Why did we change the lower limit to minus infinity?
Because that's a mistake. Thank you. Thank you very much. And if you just look at this exponential, it looks like a damped harmonic oscillator. So you know that at t tends to, for very large t, this delta, how much ever small it is going to kill it. Or extremely, that you'll always reach a t beyond that delta where it will, so you will be able to put it to 0, and or you can always choose a delta beyond which this will always converge. Okay, so that's going to be our model. So let's go back to this structure because that's easier to integrate, right? This goes down, right? So this was just to demonstrate that that actually is convergent, and delta has to be positive. So now again do the integral, limit delta tends to 0 plus, and again do the same thing, correct? Well, 1 over I omega plus I delta, and you evaluate it at t equal to plus infinity and at t equal to 0. That is mine. And this is e raised to I omega t. I actually did this integral, but I'm writing it into mixed form because this gives you the convergence better. The numerator is 0 in the top limit, right? Because you take the limit later. There's a positive number that will always kill it. And t equal to 0, the exponential goes off. So you have this to be equal to minus 1 over I, but I can use that minus to shift the I in the numerator. Okay, that's your Fourier transform of your step function. So you have a Fourier transform of the step function. But in this form, this is correct. But let's rewrite this in a slightly better way. So step function of omega in the frequency space is equal to limit delta tends to 0 plus I times omega plus I delta. That's a complex number in the denominator. To get a better feel for what this is, rationalize this, multiply this with omega plus or omega complex conjugate of this in the denominator and in the numerator. That's perfectly valid, and that is how you deal with division in complex world, right? We rationalize the denominator, and then that is how the division is defined in a complex space. So this is equal to limit delta tends to 0 plus, and this is notice I times minus I, the real part is delta, right? So this is delta plus I omega over omega square plus delta square. Right. That's your structure. I times omega is the imaginary part. I times minus I is plus 1. So that's your real part. So let's rewrite this as limit delta tends to 0 plus of delta over omega square plus delta square. So we would like to have what is the real part and what is the imaginary part. Plus I times limit of delta tends to 0 plus of omega That's your real and imaginary part. And the real part is very interesting. Okay, so that's what we want to look at. Any guesses on what is real part? Probably I mentioned it last time. What is the real part equal to? Yeah, so it's going to be a delta function. Okay, so let's see what it is, right? So real part of the Fourier transform step function is equal to, this is the real part, right? That's a familiar notation, I suppose. That's limit delta tends to 0, positive on the positive side, and that's delta over omega square delta square. This is very easily, at least you can see what this is equal to. What happens, so this is a function of omega. So let's ask what happens if omega is not equal to 0. By omega not equal to 0 means that this is a non-zero quantity. This, how much ever small this is, that there is a non-zero entity there. And then if I take the limit delta tends to 0, this will always get smaller than that in some form or the other. So you're left with limit delta going to 0 plus of delta over omega square. Right? But omega square is not 0, so that's equal to 0. That's equal to 0. If omega is not equal to 0, I think of delta function, right? But it's not very obvious still. Let's say omega is equal to 0 now. That's delta, since it is 0, so that's delta over delta square now. That's 1 over delta, so that goes to infinity. Right. Again, has the features of a delta function, right? So you see that difference, this is 1 over, so the moment omega goes away, denominator dominates. Because it's a squared. Okay, but to be a delta function, it should also satisfy the feature that if I integrate this out, so delta function should be, so remember that dx times f of x, this is some g of x, so not because I'm using f of x here for some other reason purpose. So that's delta of x minus infinity to plus infinity. That should be equal to 1. Right. So we should verify that also. Then we are pretty much sure that that's correct. So let's substitute. So we are checking that this is a delta function or not. So we will substitute that in there, right? Or better, let us forget the g of x, and this is also sufficient. The delta function has to satisfy this to be equal to 1. Right, so let's verify that. Let's not introduce the g of x, that's not necessary. So let's do g of x times delta, we are going to integrate over omega and delta over omega square plus delta square. You have to take the limit delta also, delta tends to 0 also, but it will turn out that even without that, it will work. So that's the integral. So let me substitute. Whenever I have an integral of this kind, you will substitute omega is equal to what? Delta times tangent theta maybe? So d omega is equal to secant square theta. Theta. Correct? Is that correct? So that's equal to when omega is minus infinity, right? What is theta? So it's a tangent function. It is minus pi by 2. Minus pi by 2. When it's plus, it is plus pi by 2. D omega is delta secant square theta theta, and there is another delta there. And the denominator is delta square tangent square theta plus delta square. But 1 plus tangent square theta is secant square theta. That cancels out, everything cancels out, and this is equal to pi. So everything cancels out. Delta square cancels out. 1 plus tangent square. That's the integral of d theta going from minus p pi by 2 plus pi by 2. That's just pi. But we wanted a 1, right? Delta function should have given you a 1, but what you can do is, let's put, what is a delta function? You want to put a 1 over pi. Pi, and then it's 1. So this is not a delta function, it is pi times a delta function. So this implies that limit delta tends to 0 plus of delta over omega square plus delta square is pi times a delta function of frequency. That means only omega equal to 0 contributes, right? Nothing else contributes. So that's nice. So this is pi times a delta function and frequency plus the imaginary part, we'll keep it as it is. Omega over omega square plus delta square. Okay, so that's the best we can do. That's good. Let me actually, I'll take some more space. Yeah. So let's write that here. So that's pi limit delta tends to 0 plus. Okay. Any questions at this stage? Can I erase this? Okay, so we have all the ingredients now, but now we are interested in the susceptibility function. And susceptibility function is here. That's the Fourier. We are interested in the Fourier form, like what are the conditions on this? And susceptibility function is this. Right. So let's see what is chi of omega, right? T is equal to ft. It's actually t minus t prime, but as well do it for t, and then we'll substitute equal to t prime. And we already saw in the last class that if a Fourier in the time space it is an integral convolution, Fourier convolution, then in the frequency space it's a product, like algebraic product. So it seems like it should be the opposite, and that's what will come, but let's verify that, right? So we would like to see what is chi of omega. So chi of omega, remember chi of t is the Fourier transform, right? So plus infinity dt, not d omega, over 2 pi e raised to minus I omega t, chi of omega. But the inverse of that will be chi of omega. So that's minus infinity to plus infinity. Now the dt, time integral. And that's I omega t and chi of t. But time space, it's simply a product. So introduce that in. It's minus infinity to plus infinity dt e raised to I omega t. That's step function times the function f we introduced, which is already defined in the positive of space. But we know the Fourier transform of each one of them, at least formally we know, for the step function we know perfectly what it is. But f, at least formally we know. So let's introduce that. That's minus infinity to plus infinity dt e raised to I omega t. Fourier transform of theta of t is minus infinity to plus infinity d omega over 2 pi, but I cannot use omega, right? Omega is already being used on the left-hand side. So I had introduced a new parameter, omega prime, e raised to minus I omega prime t, and the Fourier transform of the step function, which we know is this step function, or the in terms of data function, and the Fourier transform of f of t. It seems like we are complicating this, but all of this collapses. This is a standard technique that happens in Fourier transformations. This time, double prime e raised to minus I omega double prime t, and f of omega double prime. Okay. I just substituted each of its Fourier transform in there. Change the order of integral because I can do the time integral here. This the omega prime over 2 pi e raised to minus, oops, I don't want to write that. I want to do both integrals, and there is this Fourier transform of the step function, Fourier transform prime. This was a prime, right? Sorry, this was a prime. Right. Prime f of double prime, and whatever is room. So now I have taken care of this, and this. All that is the time integral can go until here. So the time integral now is minus infinity to plus infinity dt. That's e raised to time integral. So it's I of times t times omega minus omega prime, and that's minus omega double prime. We saw something very similar last time. And what is this equal to? What is that integral equal to?
2 pi times delta function.
Delta function, right? That's a delta function. So very good. It's minus infinity plus infinity. We do this in 2 steps. That's 2 pi times delta function of omega minus omega prime minus omega double prime. The 2 pi's cancel, and the delta function allows me to do one integral. So I can either do the omega prime integral, or I can do the omega double prime integral. If I do the omega double prime integral, omega double prime gets replaced. So I'll do the prime integral. So this is equal to minus infinity plus infinity prime over 2 pi. And the step function, I'm doing the prime integral. So prime gets replaced by omega minus omega double prime. And as we suggested earlier, yes, this becomes a convolution, right? Convolution is when one of them is at one point, the other one is shifted a certain amount. This was a convolution, this was a product, and this is exactly the opposite here. In the time space, it's a product, but in the Fourier space, this is a convolution. Okay, good. So that's where we are. So we have, so that's a fourth quantity we can write, fourth condition if you want. So that's the fourth, it's not really, fourth condition is that chi, yeah, that's chi of omega, right? That's chi. So let's say that's your fourth requirement. Okay. Or not requirement, like, yeah, these are 4 ingredients we have found, which will impose some conditions on the susceptibility function. Any questions? Again, overall goal is to find some constraint on the Fourier. Let me, I can still work in this flow, I guess. I can erase this. Then delete this. Actually, I would like to put this here and that here. This implies and I don't have to write double prime, so prime is sufficient. Double omega. Okay. So let's begin with first and second and see what can we conclude. So notice that f of omega has a real part and an imaginary part. So there's an f of r omega plus I times f of imaginary part of omega. In your homework, I write this as a real part of f of omega and imaginary part of f of omega. Any complex function can be written in this form, where each of this f of r and f of I is real. Right? They are real functions. Any complex function can be written in that form. So
I do have a question about
yes.
that second line under 4. What we ended on was an integral over omega double prime. So
this was
you simplify or
no. So this is a dummy variable, right?
okay.
Right.
Yeah, but okay. What I wrote down was that we still had omega minus omega or omega prime in the step function, but the other two were double prime. But I guess that's enough.
No. That was omega double prime.
Okay.
That must have been a typo when you copy it.
Okay.
Because it cannot have omega prime, right? Left hand side is omega. That is omega prime.
Right. Well, it was pulling it out of the delta function.
Yeah, when so the delta function had omega minus omega prime, omega double prime. So you replace omega prime with omega minus omega.
Right.
So there is no, wherever you see omega prime, you can replace it with omega minus omega double prime. Right? So there won't be any omega prime. So it's omega double prime.
Okay. Yeah.
Is that clear?
Yeah.
Okay. So what does this become? Let's use 1, right? So let's use 1, right? So using 1. This means that f of omega star, right? F of omega star is equal to f of minus omega. Correct? So that means f of r of omega star plus f of r omega plus I of f of I of omega star is equal to f of r minus omega plus I times f of I minus omega. That should be straightforward. This is a complex function. These are real, so only I changes sign. So that's f of r omega minus I times f of I omega. That's equal to f of r correct. Can we conclude something from here? Yes, that this is equal to this. and this is equal to minus of this, correct? So it means that, so we can conclude this implies that f of r of omega is surely an even function. And f of I of r minus omega is equal to minus of f of I omega. It means it's an odd function, correct? So the imaginary function, the imaginary part of that f has to be an odd function. But we can learn more. Now let's use the second one. So using Q now, we also know that f of minus omega has to be equal to minus of f omega, which if we put this in real and omega, so that means that's just minus of that. So this will be valid for this also, correct? So let me go slow. Okay. So f of minus omega is equal to minus of f of omega. That means that f of r of minus omega plus I times f of I of minus omega is equal to minus of f of r omega minus I of f of I of omega. So there's another condition now. I also again learned that f of r of minus omega is equal to minus of f of r omega. That seems to suggest that that's an odd function. I just now proved that that's an even function. This is an odd function according to this statement. And it's also f of I minus omega is equal to minus of f of I omega. Okay. That's an inconsistency. What does that mean? You cannot get two different, but like you cannot have an odd function and an even. It must be a mistake. Or let's assume that this is all correct.
Or it changes behavior at certain area, I think.
So if a function is both an odd function and an even function, what can you say about the function? Zero. It has to be zero, right? Now, no other possibility, right? So this implies that real part doesn't exist. Right? There is no real part of this. That's a big constraint. Okay? And f of I is imaginary. Odd. And this is true. Right? That clear? Simple, very simple argument using the first and second. So this all implies, so 1 and 2 implies, so this whole thing implies that f of omega is equal to I, or let's say 0 plus I of I omega. And in fact, this is further, this is actually odd. The odd feature can be used later. We can redefine this if you want, but we won't. Like that would be, we can further go into that, but here we won't exploit it too much. Okay. So that's your condition here open. Again, there is an implication of what you can do with the fact that this is actually odd, but I'm not going to exploit it. Okay. Good. So you're almost there. Can I erase this again? Right. So now can I erase this again? We'll do this in one board today. So we have all this implies. Okay. So what we have done is using 1 and 2. We have shown that f of omega is equal to I times I. So there's no real part to that. Okay, so let's use this in this piece now, right? Chi of omega now, similarly, chi of omega is Fourier transform, so I can write chi of r of omega plus I times chi of imaginary part of omega. That's equal to minus infinity to plus infinity omega double prime over 2 pi. Oh, we got a double prime because Moses. That's okay.
Oh, whatever.
No, it doesn't matter. Wasting ink. So, but we know step function. It's pi of delta of whatever is the argument of the step function. That's omega minus omega double prime. Right? Plus I times whatever that is there. We substitute that. So plus and omega over omega square plus delta square. It's the imaginary part. Right. And f now, f of omega double prime is I times the imaginary part of omega double prime. Correct? Oh, this should again be omega. Oh, mistakes. This is all omega minus omega. Squeeze that in now. Limit delta tends to 0 plus. That's omega, but omega is omega minus omega double prime. That's divided by omega minus omega double prime square plus delta square. Sorry for that. That's how. But we want to match our real and imaginary part. Notice this is real, right? Imaginary part of f is real. So there is I is the only feature that gets the complex part. So, oh, there was an I. Minus omega double prime plus I. Okay, sorry. Sorry for that. Introduce the I in there so that I can match these things. The first term gets an I, pi cancels out. Right? So actually, this is the real part, right? There's a minus sign, I square and a minus sign. Right? So there's a minus 1 over, so this is minus infinity to plus infinity e omega prime over 2 pi. And this whole thing, limit delta tends to 0 plus omega minus omega double prime. And f of I, omega double prime. I squared equals the minus. So that's the real part. And the imaginary part is, that's plus I cancels out, the 1 over 2 integral. Actually, I can do the integral, right? Delta function integral is always doable, easy. I just have to replace omega double prime with omega everywhere. So, omega double prime with omega, right? That's f of I omega. So we learned that the imaginary part of the susceptibility function actually is simply 1/2 times the imaginary part or half of the imaginary part of the function we introduced, of the Fourier transform of the function we introduced. And the real part, now, if that's the case, the real part of the susceptibility function is equal to this. But the imaginary part is the imaginary part of this, right? I can replace this with this. So I've learned, so there's a factor of 2 that multiplies, and so this is typically written as minus 1 over pi. Factor of 2 cancels out. Omega double prime. And let's write this as that can be simplified. Again, this was, remember, rationalized, right? So if you remove the rationalization, this can be rewritten in a way, but this is the best way to write it. Is very clear, and this has complex function features or properties of an analytic function, and this is kind of imaginary part of omega double prime. And notice that, so these two are pieces of the same function. Susceptibility is a complex function whose real part is related to the imaginary part. You can in fact invert it also. You can write imaginary part also in terms of the real part. And this is called the Kramers-Kronig relation. We are going to build in the next 2 classes, if not 2, at least in 2 classes probably. We are going to show that the imaginary part of the susceptibility function is related to how much light is absorbed by a material. Absorption, if you want, or how much light is absorbed. And the real part decides how much light is reflected or transmitted. It's called reflection, or the refractive index. Yeah, let's say refractive index. So the refractive index of a material is decided by how much light is absorbed. If you think of it as kind of a conservation theorem, like light comes in, how much light is transmitted is decided by how much light is absorbed. And it's slightly more than that. This is to do with the idea that how light gets transmitted. Light strikes something, it vibrates it. This is the idea of Faraday. It vibrates it, and those vibrations emit radiation. So that is this content in here. This shows up as optical theorem, and you're doing scattering, but this is the main idea that a disturbance has to be first transferred to something, and that will then transfer it to something else. It's not a direct, it will be called an action at a distance versus, what is it called? What's the other one? Action at a distance, and what's the opposite of it? Yeah, Newton's law is action at a distance, right? So something like Newton, when Newton talks about 2 masses, gravitational force, Moon knows about Earth's presence just magically. If you were to disappear, if you were to instantly move Earth for a second, Moon is also supposed to react immediately. Right? That's an instantaneous force. But here the idea is that that gravitational field actually takes some time to reach there, and that's this cause and effect. It takes some time. The response has a time involved in it. All those things comes in here, and we will see. We will actually now build models. Now, whatever So this is one feature. You're all going to be working in experiments or any kind of model building. If you want to write the susceptibility of a material, it has to satisfy this. If you're proposing that, oh, I have a material that satisfies something, it has to satisfy. Otherwise, you're violating some basic principle. This is a very basic causality that cannot be violated. And it is, even though it seems very simple, even half of the literature on susceptibility functions has errors, and usually it gets very controversial. So because this is hard to decipher in a sense, it's encoded in the analytic properties of complex function. But we will do simple examples. In your homework, you do 2 examples, and I will actually build models, at least 3 or 4 standard models, conductivity model, insulator models, and one which is extremely trivial. I think you see that in your homework, but we will motivate that from simple arguments using Newton's laws. See. Thank you. Yeah. So again, 2 minutes late.
Just 1
That's
minute.
improvement.
Improvement.
I just say it's just 1 minute.
It's 1 minute. Good. Better. Thank you.
Thank you.
Bye, Jordan. Bye, Khalid. Bye, Aliyah.
Bye-bye.
Bye, Jordan.